Today we are going to talking about MOSFET. The full form of MOSFET is metal oxide semiconductor field effect transistor. MOSFET is the most widely used semiconductor device in the IC industry. So basically we will talk about N-channel MOSFET because the channel region between source and drain consists of N-type materials. So there are basically 4 terminals in a MOSFET device. The first terminal is source, which is doped N plus for N channel MOSFET, and the second is drain, which is again doped and similarly as the source. There is a substrate of P type, and connected to which is the body terminal, and again there is a gate terminal which is isolated from the substrate by a thick layer of silicon dioxide, which is called the gate oxide. The length of the channel is L and the width of the device is W. So how does the MOSFET operate? If we apply a small voltage between the gate and source terminal, we'll find that due to applying positive voltage, positive charges will accumulate on the metal side of this oxide layer, and the oxide layer will act as a dielectric, and so the both end will operate as a capacitor. So due to the accumulation of positive charge in the metal side of oxide layer, the positive charges of the P substrate will diffuse to the lower portion, and the negative ions will be there, and so a depletion region will be created where there will be no positive charge carrier, only negatively charged ions. This region will be called the channel, and the creation of such a channel is called inversion. Inversion is the creation of a channel biased opposite to the substrate layer, and the minimum amount of required voltage for creation of a channel from source to drain is Vt, or threshold voltage, and the difference between VGS and Vt is called VOV, or the overdrive voltage. And the total charge Q is the product of capacitance and voltage, we all know. So capacitance equals to Cox into WL. W is the width and L is the length of the device, and VOV is equal to the overdrive voltage. Cox equals to epsilon ox, or dielectric constant of oxide, and Tox, the thickness of oxide. Tox equals to epsilon A to Kox. Kox is the dielectric constant of oxide, and epsilon naught is the permittivity in vacuum, and the unit of Cox is farad per meter square. So now the channel is created, and the current will flow provided there is a bias between source and drain. So first of all, we apply a very small bias between source and drain terminals. So for after applying the bias, find that charge by total channel length equals to Cox to W to VOV, or overdrive voltage. This is equivalent to the equation mentioned earlier, but here we are assuming the channel is not fully operational between source and drain. Okay, now again, electric field E equals to VDS by L. L is the distance between source and drain, and so any electric field E equals to VDS divided by L. Now electron drift velocity equals VD equals to mu n, which is the electron mobility. Electron mobility into E, and that is equal to mu n to VDS divided by L. And we know the drain current equals to total charge divided by time required to travel from source to drain, which is equivalent to charge divided by total channel length divided by electron drift velocity, is equal to Q by channel length into electron velocity. From the earlier equation, we found that Q by channel length equal to Cox W to VOV. Cox W into VOV, and VD equals to mu n VDS divided by L. So the drain current is mu n Cox W by L VDS VOV. We can call mu n Cox as a constant because mu n is fixed for a certain type of material like silicon, and Cox is also fixed for certain type of materials like silicon oxide and other oxides. So we can have a constant Kn dash, and Kn dash into W by L VDS into V over drive equals to the drain current for a very small VDS, which can be visualized from here. And the ID versus VDS curve is linear, and with increase of overdrive voltage, the slope of the line increases. Now we increase VDS more, but we keep in mind that VGD must be greater than VT, or VGS minus VDS must be greater than VT, or VDS must be less than VGS minus VT, which is the overdrive voltage. So what is the picture now? Channel in the source side will be operational when VGS is greater than VT, but channel in the drain side will be operational when VGD is greater than VT. But here we can find a picture that in VGS side or source side, the overdrive voltage is VOV, but in the drain side, the extra voltage is V overdrive minus VDS, which is this. This is the VGD, this is the VT. So this, the extra amount of voltage is V overdrive minus VDS. Now we know that the charge Q is proportional to channel area. which is from here we can visualize. This was the area of channel. So Q is proportional to channel area, and this is of a trapezium shape. V over drive minus VDS. This is a trapezium shape, and the area of a trapezium is proportional to half length of parallel sides. So length of parallel sides equal to V over drive plus V over drive minus VDS, or Q is proportional to V over drive minus VDS by 2. So ID equals to Kn dash W by L V over drive minus VDS by 2 into VDS. This is the second zone, and now operation for GD is less than VT. That means there is now no channel in the drain region. When VGD equals to VT, this is called pinch off condition. Pinch off condition. Now VDS saturation will be equal to VGS minus VT. From here, VDS is less than VGS minus VT for second region. For pinch off, VDS saturation equals to VGS minus VT equals to V over drive. Now again using the trapezoidal rule to determine the area of channel, Q will be proportional to half V over drive voltage. So ID will be equal to Kn dash by 2 W by L V over drive voltage square. And for any voltage above the pinch off region, the channel length will be decreased, but the total area will be constant. So the current ID will be saturated. This is the current ID said, and the current will not increase any further for an ideal MOSFET. So we can visualize the ID VDS curve for 3 regions. This is the region 1, this is the region 2, and this is the final, the region 3. This is the saturation region. Thank you for listening.